In this worked example, we'll look at a situation pretty similar to the last example in the theory part. We're sliding down a mountain, and this mountain is slightly more realistic. It's made of rock on the bottom part and ice at the top part. The glacier part at the top has a slope of about 30 degrees, and because it's made of ice, the friction coefficient there is negligible. We can assume there is no friction. The rocky part further down is steeper. It has an angle of 45 degrees and a non-zero friction coefficient. Finally, the mountain is 3 kilometers high, of which the first 2 kilometers are rock and the last 1 kilometer is ice. The question is, if you start at the top and you slide down the mountain, how fast are you going when you reach the bottom? In order to answer this question, we're going to calculate the amount of work that's done on you by the various forces that are acting on you. And the net work will be equal to the change in kinetic energy. And since you start at 0, it will give you immediately your final velocity. All right, so let's start at the top. When sliding down the ice, there is gravitational force acting on you. And of course, since you're sitting on the mountain, there's a normal force. Now, the normal force is perpendicular to the mountain, so it's not doing, and you're sliding along the surface, so the normal force is not doing any work. The gravitational force, of course, has a component along the mountain, so it is doing work. Now, there are two ways of calculating the amount of work done by the gravitational force. One is saying, well, so we have this slope of ice. We start at the top, we end at the bottom. We know that this height, h1, equals 1 kilometer, and we know that this angle theta 1 equals 30 degrees. So we can calculate this distance s1, which of course we know that the sine of theta 1 is h1 over s1, so s1 is h1 over the sine of theta 1. And the component of the gravitational force that's acting on your body as you slide down, well, gravity is of course always pointing down, not perpendicular. Gravity is pointing down and it has a component perpendicular that's not doing any work, and a component along the surface that's doing some work, and that's the interesting one. And that one is the total magnitude times the sine of theta 1. And so the work done on this part by the force of gravity is Fz times the sine of theta 1 times the distance s1, which is h1 over the sine of theta 1. So we see that the angle nicely drops out, and we get that the work done is your mass times the gravitational acceleration, because that's the force of gravity times this height h1. An expression you may recognize and we'll see again in the next lecture. We could have also guessed this by saying, well, we know that the total displacement in the vertical direction is this h1, this 1 kilometer, and that's exactly the direction that the gravitational force is working in. So we could have skipped calculating S1 and the component of the gravitational force along the surface and immediately written down m times g times h1. That works for the first part because there is only normal forces and gravitational forces here. In the second part, that no longer works because then we also have a friction force that we have to take into account. So if we look at the second part, there's now two forces that are doing work. One is the gravitational force, for which we can write down exactly the same thing, nothing has changed. So we have but we also have the frictional force. So let's take a look at the frictional force. Well, we have another slope, theta 2. We have, again, your body. We have the normal force, which we've seen before was Fz times the cosine of theta 2. We have the gravitational force, and we have the frictional force. And since we're moving, we are dealing with kinetic friction here, so now the magnitude of the frictional force equals the normal force times the coefficient of kinetic friction. So, and then plugging in what we already have here, that's the m times g times cosine theta 2 times this coefficient of kinetic friction. So the work done by friction on this part equals the friction force, uk mg cos theta 2, times the displacement, and the displacement I can calculate in exactly the same way as for the first part. It is the height divided by the sine of the angle. So it's h2 divided by the sine of theta 2. Right? It goes in exactly the same way as for S1. Now I have to be a little bit careful. This work is done by friction. It's decelerating you, whereas the work done by gravity is accelerating you. So the net work done is the first part, the gravity work on the first part, plus the gravitational work on the second part, minus the frictional work, because friction is slowing you down. So the net work is the following. It's m, so net work is mgh1 plus mgh2 minus mg, and now we have a combination. It's h2 mu k, and then we have the cosine divided by the sine, which is 1 over the tangent, also known as the cotangent of theta 2, this angle. And so we can rewrite this if we want by pulling out the mass and the gravitational acceleration, and then we have h1 plus h2 minus h2 times mu k times the cosine, so the cotangent of this angle. Does this make sense? Well, the higher the mountain gets, the more work gravity and friction can do. That makes sense. The larger the coefficient of friction, the larger the amount of work the friction force does, and therefore the less amount of work is left over for accelerating you. So this seems to be perfectly sensible. Now, what I told you is that this net work is converted to kinetic energy. We'll see that again also in the next theory part. This gives me a change in kinetic energy, and kinetic energy is given by, well, so we start at 0, so it's just the final kinetic energy, half times the mass times the final velocity squared. And so if I want to answer the original question, which is how fast are you going when you reach the bottom of the mountain, what I have to do is rewrite this. We see that the mass drops out, and we multiply the answer by 2 and take the square root, which is the final velocity is going to be the square root, I'll put that over in a second, of 2 times g times h1 plus h2 minus h2 mu k cotangent of theta 2, and then it's the square root of this whole thing. And of course I could have been given some numbers in the problem, and this is the point to start punching in those numbers in my calculator. As always, let's check if our answer is self-consistent. So in the end we want, well, we have two things that we can check. Right? We can check if the net work has dimensions of force times displacement. Well, that it does, because all three terms in parentheses in the work have units of meters, whereas the factor before is mass times gravitational acceleration. That's a force, so that's correct. And our final answer is the square root of the gravitational acceleration, which is meters per second squared, times meters, so we have meters squared per second squared, square root of that is meters per second, which indeed is a velocity. And we see that if the height gets larger of either part, the final velocity goes up, makes perfect sense, and also if the gravitational acceleration gets larger, the final velocity goes up, and that too makes perfect sense. Alright, so what have we done? We've calculated the work by chopping up the problem in bite-sized pieces. On the ice, we only had the force of gravity, it was constant there, and so we could calculate the work quite easily. On the rock, we had two forces, gravity and friction. We just simply calculated the work for each part, and since work is a number, we can then add or subtract them. And the only thing we have to be careful of is that we properly do that, because gravitational force was accelerating you, so it was doing positive work, whereas the frictional force was decelerating you, and it was subtracting from the net work. And then we used what's known as the work energy theorem. Net work is converted into kinetic energy to get our answer.